Hello. Okay, so this is problem 1 for tutorial 1. And this is your shear and moment diagrams for frames. Instead of like going into vague detail about this one in particular, what I'm going to do is I'm going to give you a fully worked example for a problem that's similar to this one, but that is not quite the same. The problem I'm going to use is this problem. This problem here. So it's essentially it's a similar problem, just with this BC part removed. Yeah, I'm going to give you a fully worked example for this one, so that this one will be a little bit longer than usual, but the other one should be a little bit shorter. And I think that if I do that, you should have a much better understanding of how to do these things. So first, let's draw our problem. We have a pin and a roller, and we'll have a 1 kilonewton force here. This is a distributed load of 1 kilonewton per meter. This is A, B, and C, where A, B, C is the frame. And these dimensions, we need dimensions. This is 0.5 meters. This is 0.5 meter. Sorry. This is 1 meter. This is 0.5 meters. Okay, and we're going to use coordinate system based here. This is X and this is Y. Okay, let's find our reactions first, as usual. We always start with our finding the reactions. So we already drew the coordinate system. That is 1 point. Well, not for the homeworks. It is for the exams, but not for the homeworks. Here, to find your reactions, let's start with sum of moments about A, using clockwise positive. So we have 1 kilonewton times 1 meter times 1/2 meter. So this is omega times length times distance, plus 1 times 0.5, and this is this. So this is distributed. This is constant. This is point. Minus by times 1 equals 0. And if you do this, you'll get by equals 1 kilonewton. Okay, I'm going to try and cut out a few steps, because last time I made this video, the video came out to be more than 20 minutes long. So we're gonna do this quickly. You have your sum of forces in the Fy direction. Okay, one note here. Note that nothing changed. This is exactly like a normal, this is exactly how you do a 2D case. You don't have to move the forces around anywhere. You can just look at this and calculate everything. The only thing that changes is that now you have extra forces, extra locations where forces can act. That's all that really changes. So when you do your sum of forces in the Fy, you have Ay plus By minus 1 kilonewton per meter times 1 equals 0. And now note that By is equal to 1, so Ay is just equal to 0. And this is perfectly fine. You can have a reaction that is equal to 0. All that means is that your loads balance out in such a way that your reaction doesn't do anything. So it's perfectly fine. And now we're going to look at this Fx case. Now when you're looking at a frame, it doesn't matter where the load is applied. You can just look what forces act in the x direction. It doesn't matter how far away they act. It's just the magnitude of the forces. And so the only thing that can resist the lateral rotation is point A. So you have Ax, and I'm going to assume that my reactions follow the x and y coordinates. So this is my Ax, my Ay. And let's say that Ax plus 1 equals 0. So Ax equals -1. That's all. Like that is your reactions. There's nothing tricky that happens here. Okay, and now, well, in order to graph the equations, in order to graph our moment in shear, we need to calculate our equations, and there are a couple things you need to do. I'm gonna pull in the class example here. Note that you need to make 3 cuts for this problem. From here to here, because these are between reactions, between point loads. Here, because you have a reaction here, you need to use another cut. So you have another reaction here, or another cut here. And then here, you change direction. You enter a different member of this frame, so you need another cut there. In our case, we only need 2 cuts. We need a cut here and a cut here. Sorry, a cut here and a cut here. Those are the only 2 cuts we need. So let's look at member AB first, and we're gonna draw this. This is 1 kilonewton meter, and this is x. Okay, and now let's draw our. We'll call this M. We'll call this V, and we'll call this A. Okay, I'll normally call axial A, but I'll call it N here because we already have A. Okay, so for our N of X, our N of X is just the forces that are acting axially. So what forces do we have acting axially? Well, we have AX, AY, and we have our AX is equal to -1. So we have well, let's write it this way: plus AX equals 0, N of X equals negative AX equals negative and -1 equals 1. And that is our axial force. And I am sorry for using red. I know red is the mind-searing color that all educators are supposed to frown upon using, but I have 4 colors, and like a professor, I must use red in this case. Let's look at shear very quickly. Shear is V of X. Okay, let's do it this way. AY minus 1 times X. This is 1 times the length, which is X. This length here is X. And X is going to be from 0 to 1. Sorry, I didn't realize I was off the page. So this is 1 times X minus V of X equals to 0. And when you do this, you get V of X, this is 0, is equal to negative X. That's all there is to that. And now moments, we have anti-clockwise positive. So we have M plus 1 times X over 2 minus AY times X, this is 0, equals 0, and we should get M equals negative X squared over 2, and to check, equals negative X. So we are okay, so these are our equations for this member. And note that was just like any other member, right? It was just like what you do for more typical for any component of any moment shear diagram you've done before. This is all ordinary. Now let's look at member BC. This is BC. We're gonna make our cut here. I'm gonna let's rotate this a little bit just to make things crystal clear. If I make my cut, I want to go from here downwards. We'll call this X prime. I'm not going to elaborate on this too much. I'll just say that it's much easier if you make your X prime go this way, because you don't need to worry about the forces that are coming from B. if I make it like this, x prime, then my cut is here. So when I look at this, I need to look at this as saying that my moment is this way. We'll call this M prime. My shear is this way. We'll call this V prime. And my axial force is this way. We'll call this T prime. Okay. So yeah. So this is you guys have done this in class many times. All I did was, because I'm going from this side, the reason why this is important is because your directions of your arrows change a little bit, and if you're not consistent, you'll get results that they might be off by a sign. That might throw you off a little bit later. So yeah, let's work with our axial force here first. In our axial force, there is no axial force, right? So T prime equals 0. Okay, that is easy. I deliberately chose tension or axial to be red because that's the least used color in this thing. V prime, well, what is V prime? V prime minus P equals 0. So V prime of x equals P. And then what about M prime? Yeah. M prime plus P of x prime. That should be prime. M prime of x equals negative x prime P. Now we can check dm prime dx prime is equal to negative P equals to negative V. And that is okay because we're on the opposite side. So these are your equations. You have these equations here, and you have your equations over here, here. And there is nothing. I hope you guys saw that there was nothing tricky about that, how that happened. Now I'm going to show you something interesting that happens here. I want you to notice the relationship. Sorry, this is not equal to P. This becomes equal to 1, and likewise this becomes equal to negative P. Equals negative x prime. I want you to notice what happens here. We'll call, yeah. What is the distance from A to B? Or sorry, when you're starting from here, what value of x gives you B? And so when x equals 1, right? Let's look at this here. M of x equals to 1. And and when you do this, you get negative 1/2. What about for M prime? M prime, the equation is right here. M prime. In our diagram, it's only 1/2, right? X equals 0.5. And then what happens when you plug this into your equation here? You get, sorry, this is kilonewton meter, equals negative 1/2 kilonewton meter. So your moments are the same, and this makes sense because there's nothing that's affecting your moment. Oh no, I drew my marker on something that I didn't want to draw my marker on. Oh well, it's okay, it's okay. It's a disaster, but it's all right. Now let's look at our shear and our axial. Our shear and our axial act, our rotation actually acts in the same direction regardless of what we're looking at because we're looking at a 2D frame. Our rotations always act out of the page. They always act out of the page or into the page, however you want to look at it. They act into the axis that we're not looking at. Our normal and our shear forces act in perpendicular directions. And so what does this mean? Look at what happened to our, let's see if I can get everything in the frame at once. I cannot. I'll show you the oldest trick in the book and just fold this like this. Okay. Let's look at these two equations. Did you see anything that is similar here? What you should see is that our shear here became our axial force here. I just want you guys to realize that should make sense, right? Like if our shear and our normal forces are perpendicular to each other, then rotating the frame by then using a member that's perpendicular to the other member, if we look at this here, then they just switch places. Sometimes the sign will change, but like they're equivalent. The reason why the shear and the axial force are not equal in this case is because we have this reaction here. We have a reaction at B, and the reaction at B is equal to 1. So if we do V of 1 equals -1 plus 1, we get 0, and 0 equals 0. So there is a relationship. Now note that this direct one-to-one relationship only applies for things that are perpendicular to each other. If we had something that was at an angle, let's call this like 45 degrees, then our axial force would have components in both directions. Let me draw this. Let me draw this the other way. If we have axial force here, then we have both axial and shear components. But in our case, we don't need to worry about that. In all the problems in this homework set, you don't need to worry about that. You just need to remember that there is a relationship between these two, and don't rely on this. In our case, for example, like you can't just use this because you have the reaction here. It makes things a little bit more complicated, but keep that in mind that there should be a correlation between those two. Now, your moment and shear diagram graphs, I'm not gonna. It's just like any other graphs that you may draw. You draw your thing up here with your loads, and then you have your thing down here. Your axial force is going to be, I believe it's equal to 1. I might be off by, oh no, let's do this properly. Yeah, your axial force is equal to 1, positive. Your shear force is equal to -x, so you're 0 at the beginning, you're -1 at the end, so it's just linear. And your moment is negative x squared over 2. So when you draw this, we're going to draw this positive. When you go all the way over to 1, you end up with 1/2, and I'm going to make this slightly larger than 1/2. I'm going to make these aren't to scale. This is minus 1/2. Okay, and then you do the same thing over here for your other member, your BC. I'm going to draw it from here to here. Remember that we're going this way. I should say like this, x. So when we draw this, your axial force in the top one is just 0. 0. Your normal force, or sorry, your shear force is going to be equal to negative or positive. It's going to be equal to +1. and your moment is gonna be equal. It's gonna be linear, and it's like, let me make sure that I did this correctly. Yeah. Your moment is gonna be linear, and it's gonna be negative from here. When you're drawing these on your diagram, you can draw these like these, but you're supposed to draw them all at once on a diagram. So you can draw 3 separate diagrams if you want. We'll call it this way, and this way. And what ends up happening is, what is blue? Blue is your moments. Is like this, and your thing is like this. Green is your shear, and your shear goes like this, and then it goes like this. Oh, sorry, your shear goes like this. And finally, your axial goes like this. Okay, so those are your diagrams. That's for this problem, but as you can see, this problem is quite similar to number 1. There's just an extra little term. There's an extra little piece, but yeah, I know this video is long, and kudos to you, to whoever manages to watch the entire thing, but it's a complete work example. The rest of them are going to be a lot shorter because of that, because I'm not going to go into nearly as much detail here, but I wanted to give you guys a full example because I felt like I think the guest lecture went a little bit over, and I think the professor did not have as much time as he would have liked to go into details about this. So yeah, I'm going to give you one fully worked example that is similar to your homework problem, but not quite the same. And yeah, I think now that you guys have seen this, you shouldn't really have too much problems, but definitely feel free to email me or come in and let us know if you have any problems. I'm going to be having office hours on Monday this week because the homework is due on Tuesday. So Monday from 4 to 6. And I'm teaching Monday lab from 2 to 4. So if I finish early, I'll be there. So Monday 4 to 6. Maybe 3 to 6. And I'll still have Tuesday from 4 to 5. So yes, as always, let me know if you have any questions. I know this is kind of late, but you guys there wasn't much time to make videos this week, so I had homework that I had to finish, and so yeah, but yeah, let us know if you have any questions.